Module 8, Lecture A, Exception Hierarchy. By the end of this lecture, you will be able to describe the structure of the built-in exception hierarchy and the roles of base exception and exception. Select appropriate built-in exception types to signal different categories of errors in your code. And use IST-instance checks to handle groups of related built-in exceptions in try-except blocks. Base exception and system exits. Base exception and exception. In Python, base exception sits at the top of the exception hierarchy and is the common ancestor of almost all runtime errors. You can think of it as the root of the entire exception system, which allows Python to treat all exceptions in a unified way while still distinguishing different kinds of problems. Directly beneath it is exception, which represents most everyday errors, such as type or value issues. In practice, base exception marks that something exceptional has happened, while exception focuses on errors that your code is typically expected to catch and handle. During a program's execution, different kinds of problems can occur, and Python organizes them using an exception hierarchy. Common issues, such as missing files or invalid data conversions, are represented by the general exception class and are meant to be handled by your code. More serious events, like a user forcibly stopping the program, are direct subclasses of base exception, which marks them as more critical than routine errors. This structure helps Python distinguish between everyday problems your program should manage and major events that can affect the entire process. In Python error handling, you usually work with the exception class and its subclasses rather than with base exception. These are the kinds of errors you expect in normal programs, such as file access problems or malformed data. And they are issues your code can handle by retrying, logging, or otherwise recovering. In contrast, some exceptions that come directly from base exception signal more serious conditions that generally should not be caught or ignored. Keeping this distinction in mind helps you separate routine application errors from broader runtime signals. Python code, base exception, and exception. This material explains the difference between the base exception and exception hierarchies in Python and how they should be used. It emphasizes that you should be careful when catching base exception because it includes very low-level events like system exit and keyboard interrupt, which you usually do not want to handle in normal code. In contrast, catching exception is safer for most application errors. The goal is to demonstrate how catching exception versus catching base exception changes which errors are intercepted, and to print out which specific exceptions are handled by each type of except block. This example shows a common programming error that occurs when trying to convert a string that does not represent a number into an integer. The code first stores a clearly non-numeric string in a variable, then attempts to convert it using the integer conversion function. Because the string is not a valid number, this conversion fails and raises a value error. This type of error appears frequently in real applications and should usually be handled so it does not cause the program to crash. This function demonstrates how a system-level signal can be simulated by manually raising a keyboard interrupt. Normally, this interrupt is triggered when a user presses Ctrl+C in a terminal. The example shows that keyboard interrupt is a direct subclass of base exception, not of the regular exception class. Because of this, it behaves differently from standard exceptions, which are usually caught by handlers that only deal with exception subclasses. We begin by noting that the code is designed to catch only exceptions that are subclasses of the general exception class. Inside the try block, we call a function that triggers a normal error by trying to convert a non-numeric string into an integer. This operation raises a value error, which is a common subclass of exception. The except block is written to catch any exception, so it successfully handles this error and prints a message indicating that a normal error occurred, along with the specific type of exception that was caught. We demonstrate how to catch exceptions at the base level, including system signals. Inside a try block, we call a function that simulates a system signal by raising a keyboard interrupt, which is a type of base exception and represents events like pressing Ctrl-C. An except block is set up to catch any base exception, so when the keyboard interrupt occurs, this block handles it. We then report that a base-level signal has been caught and show the type of exception, illustrating that catching base exception lets us handle both regular exceptions and system-level signals. This script illustrates the difference between catching exceptions that inherit from exception and those that inherit from base exception in Python. When it tries to convert a non-numeric string to an integer, a value error occurs, which is caught by handling the general exception type. The script then manually raises a keyboard interrupt to mimic a system-level signal, which is a subclass of base exception. By catching base exception, the script can handle this signal as well. Overall, it emphasizes the importance of understanding Python's exception hierarchy, especially for dealing with system-level signals that require special care. System exit and keyboard interrupt. In Python, two main exceptions tell the interpreter to stop running: system exit and keyboard interrupt. A system exit is a deliberate shutdown, usually triggered by the program when it finishes or needs to close in an orderly way. A keyboard interrupt comes from the user, such as pressing a key to stop a long-running task. These are not typical errors, but control signals that unwind the call stack, halt execution, and can return a status code to the operating system. System exit and keyboard interrupt should be seen as control signals rather than errors. A system exit is usually triggered on purpose by the program, often after finishing tasks like saving data, and it includes a status code that tells the operating system whether the run was successful. A keyboard interrupt typically comes from the user, such as when they stop a long-running script, and it will propagate unless the program handles it. Together, these exceptions act as a way for the program, the user, and the operating system to communicate about whether execution should continue or stop. System exit and keyboard interrupt exceptions are important for controlling when a program stops. In most cases, you should let them propagate so the program can end when the user or the program itself decides to quit. You may catch them briefly to perform cleanup or logging before shutdown, but you must not hide them completely or the program can appear frozen. Treating these exceptions as normal control signals rather than errors helps you design exception handling that respects user intent and supports a clean, predictable shutdown. Python code, system exit, and keyboard interrupt. System exit and keyboard interrupt are special exceptions used as control signals to stop a Python program. System exit is raised to end the script on purpose and can carry a status code that indicates success or failure to the operating system. Keyboard interrupt is raised when the user interrupts the program, for example, with a key press. You can catch keyboard interrupt briefly to perform any quick cleanup or logging, and then re-raise it so the program stops cleanly. We begin by importing the time module so the program can work with time-related features, such as pausing execution. We also import the system module, which gives access to system-specific settings and functions. Together, these imports prepare the script to handle timing tasks and interact with the underlying system as it runs. This script demonstrates how special stop exceptions can control a program's flow. It begins by explaining that it will intentionally trigger a system exit exception. This shows how a program can be deliberately stopped using system exit, often with a chosen status code. The goal is to help you understand how such an exception can be used to end a script in a controlled way. In this example, we enter a try block and deliberately raise a system exit exception with a status code of 2 to simulate an intentional stop in the script. We then catch this system exit in an except block, where we print a message saying that the exception was caught and show its status code. This illustrates that you can intercept a system exit exception to run specific code, such as logging or cleanup, before the script actually stops. After catching the system exit exception, the script continues running and prints a message to show that this behavior is intentional. It then sets up a situation where a long-running task could be interrupted by the user. This is used to demonstrate how to handle a keyboard interrupt, similar to when someone presses Ctrl+C to stop the program during execution. The focus is on showing that the program can manage this interruption gracefully and continue or exit in a controlled way. In this example, we use a try block to simulate a user interrupting a long-running task. We print a message, pause the program briefly using a time delay, and then manually raise a keyboard interrupt to mimic the user pressing Ctrl+C. In the except block, we catch this interrupt so we can perform any quick cleanup and print a message indicating that we are handling it. Finally, we re-raise the keyboard interrupt so the program can stop cleanly and any higher-level exception handling can take over if needed. This material explains how to handle two special exceptions in Python: system exit and keyboard interrupt. The script first raises a system exit with a status code, catches it, and continues running, showing how you can intentionally stop a program while controlling its exit status. It then simulates a long-running task that a user might interrupt, raises a keyboard interrupt, and catches it to perform cleanup before letting the interruption stop the program. Overall, it demonstrates how to manage both planned exits and user interruptions, so a script can either continue or terminate cleanly. End. Avoid catching base exception. In Python, you should not catch the top-level base exception because it is reserved for critical events like user interrupts or system shutdown signals. Catching it can block these important signals and prevent your program or service from shutting down when it should. Instead, catch specific exceptions that inherit from the regular exception class. This lets you handle normal errors while still allowing the system to manage critical shutdown behavior correctly. Catching the base exception type can cause serious problems in real programs. If you catch it too broadly, your code may ignore user interrupts, making a command line application processing large files appear frozen. It can also prevent automated systems from shutting down cleanly, which may lead them to misread the program's state and risk data corruption. To avoid these issues, you should catch only the specific exceptions you expect, so that critical stop signals are honored and the program behaves predictably. Handle only the exceptions that represent real errors you intend to manage, and let system-level exceptions derived from base exception pass through. In practice, this means focusing your error handling on the general exception type and its specific subclasses, such as those for invalid input or network failures. Allowing base exception to propagate ensures the interpreter can still terminate when necessary. Similar to how critical systems like hospital software must respond to shutdown commands. By keeping base exception out of your custom handling, you maintain clear error management while respecting important stop signals. Python code. Avoid catching base exception. Catching base exception in a simple script is dangerous because it also captures system-level events that should usually stop the program, such as a keyboard interrupt. When you wrap your code in a handler that catches base exception, pressing Ctrl+C may no longer interrupt the script, because the interrupt is swallowed by the overly broad handler. This makes the program hard to stop and can hide important problems. A safer approach is to catch the standard exception type instead, which handles most runtime errors while still allowing keyboard interrupts and other critical signals to behave as expected. The script starts by importing the time module, which provides functions for working with time. In this program, it is used to pause execution for a set number of seconds. These pauses create delays inside loops, which helps simulate a running process. This setup also makes it possible to interrupt the process while it appears to be running. This function begins by announcing that it is starting an unsafe loop and invites the user to press Ctrl+C to interrupt it. Inside a try block, it runs a short loop that prints the current second and pauses briefly each time. If any exception occurs, including a keyboard interrupt or other system exit signal, the except block catches it using the most general exception type, base exception. It then prints a message saying a base exception was caught and shows the type of the error, effectively ignoring shutdown signals while still revealing what kind of exception occurred. This function starts by announcing a safe loop and noting that the user can interrupt it. Inside a try block, it runs a short loop over 3 seconds, printing the current second and pausing briefly each time. If something goes wrong during this process, Control moves to the except block, which catches standard exceptions. There, it reports that a normal exception occurred and that expected problems are being handled. and it shows the type of error to indicate what went wrong. We begin by running an unsafe loop that catches every kind of exception, including base exceptions, to show why this is risky. This loop runs for a few seconds and even intercepts system exit signals, which is generally a bad idea because it prevents critical events from stopping the program. After that, we switch to a safer loop that only catches standard exceptions. This approach is better because it still handles common errors but allows important exceptions, such as keyboard interrupts, to pass through. By comparing these two loops, we demonstrate a more appropriate way to handle exceptions in Python. This script shows why catching the base exception type in Python is dangerous. In the first loop, all exceptions are caught, including system exit signals like a keyboard interrupt. So pressing Ctrl-C does not stop the program, and it keeps running. This is risky because it blocks proper shutdown. In the second loop, only normal exceptions are caught, so a keyboard interrupt still stops the program as expected. The example demonstrates that you should catch the regular exception type instead of base exception to avoid ignoring critical signals. Choosing built-in errors. Type versus value errors. When designing error reporting in your program, clearly distinguish type errors from value errors. A type error happens when an object is conceptually wrong for the operation, such as passing a number to something that expects text. This means the object violates the expected type, much like presenting a loyalty card instead of a photo ID. Use type errors specifically to signal that the wrong kind of object was provided, so it is clear what types are acceptable. A value error happens when something is the correct type but has an invalid value for the operation being performed. For example, a function might expect a date written as text, but if the month in that text does not exist, the problem is with the value, not the type. Raising a value error signals that the kind of data was acceptable, yet the specific content was not valid for that situation. It is like submitting the right document, such as a passport, but with an expiration date that has already passed. Choosing between type errors and value errors shapes how failures in your code are understood and fixed. A type error means an argument is conceptually the wrong kind, while a value error means the argument is the right kind but has invalid content. For instance, in a financial context, using text where a number is required would be a type error, whereas a negative principle that is not allowed would be a value error. Being consistent about this distinction makes your code more predictable, easier to debug, and clearer for both others and your future self. Python code type versus value errors. This lesson shows the difference between a type error and a value error using simple functions. A type error happens when the argument you pass is the wrong kind of thing for the operation, such as using a category of input that the function cannot work with at all. A value error happens when the argument is of the correct general type, but the specific value it contains is not acceptable for that operation. By contrasting these two situations, you can see how they signal different kinds of problems in function inputs. The script starts by importing the date class from the datetime module, which provides tools for working with dates. This class lets the program create and compare date objects. In this case, it is used to compare today's date with a specified birthday. By doing this, the script can calculate how many days remain until that birthday. This function is designed to calculate how many days remain until a birthday using a month-day input written as a string. At the start, it checks whether the input is actually a string. If the input is not a string, the function raises a type error and explains that the value must be a string in the correct month-day format. This early check helps ensure that only properly formatted inputs are processed and prevents errors later in the code. The code tries to split the birthday string into two parts using a hyphen, assuming the format is month-day. If this split does not work, it means the string does not follow the expected mm-dd pattern. In that case, it raises a value error with a clear message about the required format. The original error is attached to this new error so that the full context of what went wrong is preserved. The code takes the month and date parts of the birthday, which are in text form, and converts them into integers. It first turns the month text into a month number so the program can compare and calculate with it. Then it does the same for the day text, turning it into a day number. Converting both values to integers makes them suitable for validation and any further date calculations. The code first checks whether the month number is between 1 and 12. If the month is outside this valid range, it raises a value error to indicate that the month must be within these limits. This validation step ensures the month part of the date is correct before any further calculations are performed. The code verifies that a given day number is between 1 and 31, which is the valid range for days in a month. If the day is outside this range, it raises a value error with a clear message stating that the day must be between 1 and 31 inclusive. This check ensures that the input represents a valid calendar day and helps prevent problems later when the program works with dates. We first use the date module's today function to get the current date, and from that date object, we extract the current year. Knowing the current year is important because it lets us figure out how many days remain until the next time a specific date occurs. This could be used, for example, to calculate the days until a birthday later this year, or if it has already passed in the next year. The code creates a date for the birthday in the current year using the given month and day, then compares it to today's date. If that birthday date is already in the past, it updates the year to the next year, so the birthday is always set in the future. This adjustment ensures that when the program calculates how many days remain until the birthday, the result is accurate, whether the birthday has already happened this year or not. This code finds how many days are left until a birthday by comparing dates. It takes the birthday date for the current year and subtracts today's date, which produces a time difference. From this time difference, it extracts the number of days. That number represents the days remaining until the birthday, and the code returns it as the final result. We first print a short message to let the user know we are about to show an example with a correct input. Then we call the function that calculates how many days remain until a birthday, using the date December 25th in month-day format as the input. The function processes this valid date and returns the number of days until the next time that date occurs. Finally, we print that result to demonstrate how the function behaves with a proper, well-formed argument. We begin by announcing that we are about to show a case where the input type is correct, but the value is invalid. We then call the function that calculates days until a birthday, giving it a date string that represents an impossible month and day. This causes a value error because the date values are outside the allowed ranges. Using a try-except block, we catch this error and print a message with the error details, demonstrating that the function handles invalid input values in a controlled and informative way. We demonstrate what happens when a function receives an input of the wrong type. The function is supposed to calculate the number of days until a birthday and expects the date as a string, but we deliberately pass an integer instead. Because the function checks that its input is a string, this triggers a type error. We wrap the call in a try-except block, catch the type error, and then print a message that includes the error details to show how the function responds to invalid input. This script uses a birthday countdown function to show the difference between type errors and value errors. It first runs correctly with a valid date string, then produces a value error when given a date string whose month and day are not valid. Finally, it triggers a type error by passing a number instead of a string. The key idea is that type errors happen when the input is the wrong kind of data, while value errors happen when the input is the right kind of data type but contains invalid information. Indexing and lookup errors. When working with collections like lists, strings, or dictionaries, it is important to use the right kind of error when something is missing. If you try to access a list or string position that does not exist, you should raise an index error to show that the requested position is out of range. If you look up a key in a dictionary that is not there, you should raise a key error to show that the key is missing, even though the dictionary itself is valid. Using these specific exceptions correctly makes your code more predictable and easier for others to read and understand. Understanding the difference between index-based and key-based lookup errors is important when working with structured data. An index error means your code tried to access a position in a list that does not exist, so the sequence is shorter than expected. A key error means your code asked for a setting or value in a dictionary-like structure that has no entry with that name. Recognizing this distinction helps you see whether you are dealing with a structural problem in the data or a missing entry, and it keeps your error handling aligned with the data model. Choosing specific error types, such as index errors or key errors, improves error handling by enabling targeted recovery strategies. Catching an index error helps when positions are out of range, allowing you to provide a default value or record a warning. Catching a key error is useful when a key is missing, so you can supply default settings or create a new entry. In complex systems with custom collections, preserving these specific errors instead of converting them to a general error keeps important information about what went wrong. This makes errors more informative signals that guide developers and users toward effective ways to recover. Python code, indexing, and lookup errors. This material explains how different Python errors signal different kinds of missing data problems. It shows that index errors occur when you try to access a list position that does not exist, while key errors occur when you look up a dictionary entry using a key that is not present. By comparing these exceptions, you learn how each one describes a specific failure in indexing or lookup. This helps you choose the correct error type and better understand what went wrong when working with lists and dictionaries. We begin with a list of 3 temperature readings in Fahrenheit to represent data collected from sensors. We also create a configuration dictionary that stores options such as language and theme, each paired with a specific value. Together, these examples show how Python can store different kinds of information using lists and dictionaries. With these structures in place, we are then ready to examine what happens when we try to access data that is not actually there and how that can lead to errors. The code first prints the current list of temperature readings in Fahrenheit, so you can confirm the data being used. It then prints the configuration settings stored in a dictionary, such as language and theme. Together, these outputs let you verify both the sensor data and the setup that may affect how the program behaves. When we try to access the 4th element in a list of sensor readings, we are actually using an index that does not exist because lists start counting from 0. This causes Python to raise an index error. To handle this safely, we place the access inside a try block and catch the index error in an except block. This lets us print a clear message about the problem and allows the program to keep running instead of crashing when an invalid list position is used. When we try to read the timeout setting from a configuration dictionary and that key is not present, Python raises a key error. We catch this error with an exception handling block, so the program does not crash. Instead, we can print a clear message explaining that the key is missing from the dictionary. This shows how key error signals that a requested key does not exist in a mapping collection and how exception handling lets us respond gracefully. This summary highlights the main lesson about choosing the correct error type when working with different data structures. For lists, an index error should be used when an index is invalid or out of range. For dictionaries, a key error is appropriate when a requested key does not exist. Understanding this distinction helps you handle exceptions correctly based on how the data is accessed. This script shows how Python reports and handles errors when you access data in lists and dictionaries. It first works with a list of sensor readings and a dictionary of configuration settings, then deliberately tries to read a list element beyond the valid range, which raises an index error. It also tries to access a configuration key that does not exist, which raises a key error. Together, these examples highlight that index errors signal invalid positions in ordered data, while key errors signal missing keys in mappings, helping programmers choose the correct error type for different data access problems. Runtime and system errors. When handling errors in your programs, distinguish between mistakes in your own logic and exceptions caused by the runtime or Python itself. Runtime and system exceptions usually indicate conditions beyond your control, such as running out of memory or hitting recursion limits. These often point to deeper operating system or hardware problems, so you should not catch them casually. Only handle them when you specifically need to deal with low-level failures. For example, to clean up resources or log critical information before the program stops. When a recursive function hits the interpreter's recursion limit, it exposes a runtime error that reflects both your code design and system constraints. This usually occurs in very deep recursion, such as large tree traversals, and signals that the current recursive approach may not be appropriate. During development, it is better to let this error occur so you can redesign the algorithm, for example, by using an iterative method or breaking the task into smaller parts. In production, simply catching this exception to keep the program running can hide deeper structural problems and lead to unstable or inefficient behavior. When your program encounters severe system-level exceptions, you must decide whether it can safely recover or should stop. For less critical issues, such as a user interrupting a long-running task, the program should handle this gracefully by saving progress and closing resources. For more serious problems, like running out of memory or the interpreter shutting down, it is usually safer to let the program terminate. In these cases, treat the exception as a signal of serious failure and rely on external tools or systems to restart or recover the application. Python code, runtime, and system errors. This topic focuses on briefly demonstrating how to handle runtime and system-related exceptions in a safe and controlled way. You should be able to show what happens when a recursion limit is exceeded and how to respond to that error, as well as how to handle a keyboard interrupt so the program can shut down gracefully instead of crashing. Throughout these examples, it is important to stress that you should not blindly catch every possible base exception type, because that can hide real problems and make debugging much harder. Instead, handle only the specific exceptions you'll expect and understand, especially for system-level events like recursion errors and user interrupts. The code first imports the system module, which lets the program access system-specific settings and functions, such as checking the current recursion limit. It also imports the time module, which allows the program to pause for a given number of seconds. Together, these modules enable the program to interact with system-level features and control the timing of its execution. The recursive depth counter function takes the current depth and a maximum depth and uses them to control how far the recursion goes. It first checks whether the current depth has reached or passed the maximum. If it has, it reports that the safe depth limit is reached and returns the current depth, ending the recursion. If the current depth is still below the maximum, the function calls itself again with the depth increased by 1, repeating this process until the maximum depth is reached. The demonstrate recursion limit function first reports the current recursion limit, which tells us how many nested function calls are allowed before Python stops with an error. It then tries to reach a deep recursion, starting from 0 and aiming for a depth of 1000 inside a try block. If this triggers a recursion error because the call stack goes too deep, the function catches that specific exception. It prints a message suggesting the algorithm may need to be redesigned, along with the actual error message. This example shows how handling specific exceptions makes code more robust and easier to maintain. This function runs a long loop that simulates 10 seconds of work, announcing its start and pausing for 1 second during each step. It uses a try block so that if the user presses Ctrl+C, a keyboard interrupt is caught instead of crashing the program. When this happens, it prints a message that it is shutting down gracefully. In all cases, whether interrupted or not, it finally prints a cleanup message to indicate that the program is exiting safely. The code first checks whether it is being run as the main program so that the following actions only occur when it is not imported as a module. It then calls a function that demonstrates how Python handles reaching the recursion limit by attempting a very deep recursive call. After that, it calls another function that simulates a long-running process to show how a keyboard interrupt, such as pressing Ctrl+C, can be handled. This example illustrates how the program can respond gracefully to user interruptions and perform any needed cleanup before exiting. This material explains how to handle runtime and system-related exceptions in Python. It shows what happens when a recursive function goes too deep and hits the system's recursion limit, and how a recursion error signals that the algorithm may need to be changed. It then demonstrates a long-running process that the user can interrupt with the keyboard, and how to catch the resulting keyboard interrupt to perform cleanup before stopping. Overall, it emphasizes handling specific exceptions carefully instead of catching everything, so programs remain robust and user-friendly. Catching related exceptions. Grouping exceptions with tuples. When several exceptions represent the same kind of problem, it is more efficient to handle them together instead of writing separate handlers for each one. You can group related exception types into a tuple, which serves as a small collection of similar error classes. For example, when reading a file, a missing file, a permission issue, or an invalid path can all be treated as file read errors. By grouping them, you can use one block of logic to respond consistently, such as logging what went wrong and asking the user to choose a different file. Grouping exceptions is helpful when you want to see if an error belongs to a set of acceptable types and handle them all in the same way. Instead of writing separate logic for each specific error, you treat related errors as one family that shares a common response. For example, different problems with user input in a web app, such as wrong formats or values that are out of range, can all be treated as invalid input. You can then send them to a single handler that shows a clear error message, records what went wrong, and stops processing the bad input. Grouping related exceptions into categories such as input validation or resource access errors makes error handling more organized and easier to maintain. Instead of scattering many specific handlers throughout your code, you connect each category to a set of related exceptions. This clearly shows which parts of the code deal with issues like network failures or data conversion problems. It also makes it simpler to extend your program, because you can add new exceptions to the appropriate group and keep handling consistent. Over time, this leads to more concise, clearer, and more robust error handling that systematically covers whole classes of failures. Python code, grouping exceptions with tuples. This example shows how to group related exceptions using a tuple so that one handler can catch several input-related errors at once. Instead of writing a separate handler for each possible input problem, you place the different error types together in a single group. The program then uses one try and accept structure to respond to any of those grouped errors in the same simple way. This keeps the code beginner-friendly, short, and easy to read while still handling multiple input issues correctly. We are creating a helper function that converts a piece of text into a positive integer, but this process can raise different kinds of errors, such as when the text is not a valid number or is the wrong type. To handle these problems cleanly, we group the related exceptions together in a single tuple. This lets us catch and manage all of them with one error handler. As a result, our error handling code stays concise, organized, and consistent. We begin by importing several type tools that help us describe data more precisely. A tuple type lets us define a fixed collection of items in a specific order, which is useful for grouping related exceptions. A union type indicates that a value can be one of several possible types, such as an integer or a string. The any type is more flexible and means a variable can hold a value of any type. Together, these imports provide a structured way to handle different data types and exceptions in our code. In this section, we group several related exception classes into a single tuple to handle conversion errors in user input. This group includes value error for invalid digits, type error for inputs of the wrong type, and overflow error for numbers too large to be converted to integers. By collecting these exceptions together, we can use one error handler to manage multiple kinds of invalid or unusable input. This keeps our error handling code concise, organized, and consistent. We create a tuple called conversion errors to group several exception classes that can occur when turning user input into an integer. This group includes value error when the input is not a valid number, type error when the input has the wrong type, and overflow error when the number is too large to process. By collecting these related exceptions together, we can catch and handle all of them in a single exception block. This makes the error handling code more concise and easier to manage. This function tries to turn a piece of text into a positive whole number. It first attempts to convert the text to an integer, then checks whether the result is greater than 0. If the number is 0 or negative, it raises a value error with a clear message. If any of several possible errors occur during the conversion, the function catches them in one combined error handling block and returns a message that the input is invalid, including the type of error. This unified handling of related exceptions makes the code shorter and easier to maintain. The function called toPositiveInt converts an input value into a positive whole number and enforces that it must be greater than 0. It first tries to turn the input text into an integer, then checks whether the result is positive, raising a value error if it is not. If the conversion fails for reasons such as an invalid value, a wrong type, or an overflow, these exceptions are caught together in one place. The function then returns a message that includes the type of error, explaining why the conversion did not succeed and simplifying the overall error handling. The code tries to turn the input text into an integer and then checks whether the result is positive. If the number is 0 or negative, it raises a value error to indicate that a positive number is required. If converting the input fails for reasons such as a value error, type error, or overflow error, the code catches the problem and returns a message saying the input is invalid, along with the type of error that occurred. We create a list of test values that are likely to cause different exceptions, such as a string of letters, a very large number, a negative number, and a value of none. All of these are meant to be handled by the same grouped exception handler. Only a properly formed positive integer should be converted successfully without raising an error. This setup lets us verify that the exception handling works correctly for invalid inputs, while allowing valid input to pass through. We create a list of sample values that includes a number written as text, some letters, a very large number, a negative number, and a none value. This list is designed to provide a variety of problematic inputs when we try to convert them into positive integers. By using these diverse samples, we can trigger different kinds of errors and show how a grouped exception handler responds to each one. The goal is to demonstrate consistent and organized error handling for many types of invalid input. We loop through each sample value and try to convert it to a positive integer using the conversion function defined earlier. This function either returns the converted integer or an error message if the conversion fails. After each attempt, we print the original value together with the result. This shows how a grouped exception handler can give a single, consistent response to different kinds of input errors, while keeping the output clear and concise. We process each sample in the list by calling a function that tries to convert the text into a positive integer. This function uses a grouped set of exceptions so that different kinds of input errors are handled in the same way. After the conversion attempt, we print the original value along with either the resulting integer or an error message describing what went wrong. This shows how grouping related exceptions can simplify error handling while keeping the output clear and informative. This script shows how to handle several related errors in Python using a single grouped exception handler. It defines a function that tries to turn different kinds of input into positive integers and then checks whether the result is valid. If the input is invalid, such as a non-numeric string, a very large number, a negative value, or a missing value, the function catches value errors, type errors, and overflow errors together. Valid inputs, like the string 42, are converted successfully, while invalid ones produce a message describing the error. This approach simplifies error handling by combining multiple exception types into one concise block of code. Ordering except clauses. The order of exception handlers matters because the system checks them from top to bottom and runs only the first one that matches, including matches through inheritance. If a general handler appears before a more specific one, it will catch the exception first, and the specific handler will never run. To avoid this, always place the most specific handlers first, and the more general ones later. This is especially important when using instance checks, because a broad check too early can block more precise logic from executing. When handling errors in a data processing service, you should treat different problems, such as file issues, network failures, and programming bugs, in different ways. If a general error handler is placed before a more specific one, it will catch the exception first and prevent the specialized handler from running. This can also happen when grouping exceptions in tuples, where a broad group can overshadow a more precise case. To ensure you can respond appropriately, such as retrying a network request or logging a programming error, always order your handlers from the most specific to the most general. Exception handling should be organized in layers, from the most specific to the most general. Handle specific problems, such as missing configuration or invalid input, as close as possible to where they occur. Then, use broader handlers for related categories, like validation errors or network timeouts, often grouped with type checks. Finally, add a general outer handler to catch anything unexpected, log it, and shut down gracefully. If you put the broad handler first, it will capture all errors before the specific ones can act, reducing useful error information and missing chances to recover. Python code, ordering except clauses. This lesson shows why the order of exception handlers matters. When a broad, general handler is placed before more specific handlers, it can catch errors first and prevent the specific handlers from ever running. This effectively hides the more precise handling you intended. By reordering the handlers so that specific exceptions are listed before the general one, you ensure that each type of error is handled as accurately and appropriately as possible. This line creates a custom error class named data error that inherits from the standard exception class. By defining this specific type of exception, we mark certain problems as data-related issues. This makes it easier to distinguish data problems from other errors in our program. As a result, we can handle data errors more precisely and respond to them in a more appropriate way. This line creates a new exception class called missing field error that inherits from the more general data error class. By making it a specialized version of data error, it represents errors specifically related to missing data fields. This design lets you distinguish missing field problems from other data issues. As a result, you can catch and handle this particular error type separately in your exception handling logic. The function called processRecordBad is intentionally written to show a common mistake in exception handling order. It checks a record for a missing name field and raises a missing field error, which is a specific kind of data error. Because the first exception handler is for the general data error, it catches the missing field error before the more specific handler can run. As a result, the handler meant for missing field error is never reached. This example demonstrates that placing a broad exception handler before a more specific one prevents the specific exception from being handled properly. This function processes a record and demonstrates the correct order of exception handlers for clear error handling. It first runs code that checks whether the name field is missing, and if so, raises a custom missing field error to signal that a required field is absent. The first handler catches this specific missing field error and reports that its handler was triggered, along with the error type. A second, more general handler catches any data error and reports that its handler was triggered and what type of error occurred. By placing the specific handler before the more general one, the function ensures that precise exceptions are handled appropriately before broader errors are considered. We create a dictionary called bad record that includes an age of 30 and a height of 70 inches, but it deliberately leaves out the name field. This missing name makes the record incomplete and is used to trigger a custom error called missing field error. By causing this specific error on purpose, we can clearly demonstrate how the exception handling code responds. It also helps show why the order of different exception handlers matters when processing invalid or incomplete data. The code first announces that it is about to run a function with incorrectly ordered exception handlers, setting the stage for the example. It then calls a record processing function that has been deliberately written with a flawed order of exception handling blocks. This function is given a sample record missing a required field, which triggers the exception handling logic. The key point is to demonstrate how placing a general exception handler before a more specific one causes the general handler to catch the error first, which is not the desired behavior. We now run the function that uses the correct ordering of exception handlers to show how exceptions should be handled. The function processes a record and is written so that specific exceptions are caught before more general ones. We pass in a record that is missing the name field, which triggers the specific missing field exception. This lets us see that the function correctly identifies and handles the specific error, illustrating why exception handlers must be ordered from the most specific to the most general. This script shows why the order of exception handlers in Python matters. It uses a custom error hierarchy, with a general data error and a more specific missing field error. In the first version of the record processing function, the general data error is caught before the specific missing field error, so the more precise problem is hidden. In the improved version, the missing field error is handled first, allowing the program to report the exact issue. The example demonstrates that exception handlers should be ordered from the most specific to the most general to ensure accurate error detection and reporting. Avoiding bare except. When grouping exceptions, avoid using a catch-all handler that grabs every error, because it undermines structured exception handling. A bare handler treats minor issues and critical failures the same way, which makes debugging and understanding program behavior much harder. Instead, you should identify and handle the specific exceptions you expect, so that routine problems are managed cleanly, while serious errors are still visible and can be addressed properly. When handling exceptions, focus only on the specific problems you realistically expect in that block of code. For example, during file operations, you might group and handle missing files and permission errors together. Avoid catching unrelated issues such as logic errors, because those usually indicate deeper bugs that should not be silently handled. By using clear exception types and checking for particular instances, you make your intent obvious and allow unexpected errors to surface so they can be properly investigated and fixed. Avoiding catch-all exception handlers leads to better observability and more reliable error handling. By catching only the specific exceptions you expect, you can log them with useful context, show clear messages to users, and apply targeted fallback actions such as retries. This also ensures that truly unexpected errors are not silently swallowed, but instead surface as clear error reports. In complex systems, this is crucial because broad exception handling can hide serious issues like data corruption or security problems. Using explicit exception types and thoughtful grouping gives you precise control over how errors are handled and results in more robust, maintainable software. Python code, avoiding bare except. Bare except handlers are dangerous because they catch every possible error, including ones you did not intend to handle, which can hide real bugs and make debugging very difficult. Instead, you should catch specific exception types so that only the errors you expect are handled, and all others can still surface. Using checks, like asking whether an error is an instance of a particular exception type, lets you respond differently to different problems in a controlled way. Comparing outputs from code that uses a bare except with code that uses explicit exception handling shows that the bare version often swallows important error information, while the explicit version makes failures clearer and behavior more predictable. The script starts by importing the math library so it can use built-in mathematical functions and constants. This is important because the later functions in the code rely on these tools. In particular, the math library provides the square root function, which is essential for the calculations the script performs. Using this library helps the code carry out these operations efficiently and accurately. This function divides a numerator by a denominator, and then takes the square root of the result inside a try block. If anything goes wrong during the division or square root, a bare except block catches the error, prints a generic message, and returns -1.0 as a default value. Because it catches every possible exception without specifying which ones to handle, it can hide serious bugs and make real problems harder to detect and fix. The safe divide and square root function first tries to divide the numerator by the denominator, then takes the square root of that result. If this process raises an expected numeric error, such as division by 0, a value error, or a type error, it reports that an expected numeric problem occurred and returns -1.0 as a fallback value. If the error is not one of these known numeric issues, the function does not handle it and instead lets the exception continue to propagate. We first announce that we are about to call a function named unsafe divide and square root with a denominator of 0 to set the context. Then we actually call this function using 10 as the numerator and 0 as the denominator. The purpose of this call is to demonstrate the danger of using a bare except clause, which can catch every kind of exception, including ones we did not intend to handle. Finally, we print the function's result to observe how it behaves when a division by 0 occurs. In this example, we call the safe divide and square root function using 10 as the numerator and 0 as the denominator, then print its result. Because the function is designed to handle numeric errors, it detects the division by 0 and does not crash. Instead, it prints a message indicating the expected numeric problem and returns a default value of -1.0. This script shows why using a bare except clause in Python is unsafe. In the unsafe version, any error, including ones unrelated to division by 0, is caught and replaced with a simple message and a default value of -1, which can hide real problems and make debugging hard. The safer version instead catches only specific expected errors such as division by 0, value errors, and type errors, and handles them with the same message and default value. If an unexpected error occurs, it is re-raised so it can be properly investigated. This targeted approach makes error handling more robust and transparent. In this lecture, you learn to describe the structure of the built-in exception hierarchy and the roles of base exception and exception. Select appropriate built-in exception types to signal different categories of errors in your code. And use instance checks to handle groups of related built-in exceptions in try-except blocks. In the next lecture, Lecture B, we will go over raising and handling.
Thank you for your attention. See you all in the next lecture.